you are hearing me clearly. Can everyone confirm if you are hearing me clearly?
Yes, we can hear you.
Okay, thank you so much. Thank you for confirming that. I want to welcome everyone to my lecture today. Like I said, today's lecture is actually going to be held online because I have the understanding that some students are actually traveling for the Thanksgiving. I also want to use this opportunity to say happy Thanksgiving period to everyone. Okay, so we started logistic regression the other time. Today's lecture is also going to center on logistic regression. Uh, specifically today, the lecture is going to be how to estimate model coefficients. You remember in class on Monday, I walk you through how to, implement logistic regression using the R software. But the essence of today's lecture is just to explain, what go on behind the scene. I'm going to say that again. The essence of today's lecture is just to unravel the mystery behind the scene on what statistical method was actually used in estimating parameters of the logistic regression model. So that is going to be the focus today. Even though you know how to run the code in R, but it become necessary to also understand the method of statistics that was actually used in estimating the model coefficient. Okay, and as a reminder, I actually told you before that we use logistic regression in a situation where we're trying to characterize relationship among variables in such a way that the response variable is categorical. I remember when I started the other time, I walk you through an example where a rocket was launched and the O-ring was found damaged. And we're trying to look at the effect of temperature on the probability that the O-ring will be damaged or not. Now, when I told you the other time that we got two ways of presenting logistic regression model after fitting. One of the first way to present logistic regression is to have it in a logit form, which in a log odd form. Okay, the logit form is actually called a log or log odds form. But right now, we also have another way of presenting logistic regression model. We can actually present that in a probability form. Now, if you take a look at what I'm trying to show you now, okay, this is a way to present that in a probability form. Okay, presenting that in a probability form is basically going to be y cap. The y cap here actually represents the probability of damage. Okay, the y cap is actually going to be the probability of the characteristics of interest. So that is equal to 1 divided by 1 plus exponential raised to power minus the beta naught plus the beta 1x. Now the takeaway, what I'm trying to show you now is actually a way to, present logistic regression results in a probability form. Okay, I'm going to say that again. If you're looking for a way to present logistic regression in a probability form, it is this guy here. All what you just need to do is to plug in. You remember in class when I was trying to derive, this is what I was trying to derive. You don't need to derive that. All what you just need to do to plug in, what is your beta known, what is your beta one from the regression output. And of course, that will actually give you the probability. You are relating the probability of the characteristics of interest to the predictor. Okay, so when you take a look at, we run that in R, as you can see, the code, okay, and the summary, we have this result. Take a look at that. That is the result that we got in R, using the R. Okay, this is the result that we got in R. Now, if I want to write this now in probability form, of course, the beta naught is that guy, the beta one is that guy. That's why I label them like that. Now, if I want to write logistic regression in probability form, this is what I'm going to write. Okay, what am I using now? I'm actually using, I'm going to show you, I'm using this guy here. Okay, so that is writing logistic regression in probability form. Okay, can you guys confirm if you're seeing what I'm writing? Can you see that?
Yes.
Thank you so much. Thank you for confirming that. Okay, so after plugging in the estimate, this is what we have right now. That's a probability model. Okay, if you take a look at that now, okay, so that is actually the logistic, the probability way of presenting the logistic regression, model. Okay, so that is how to do that in R. Okay, and we wrote the model how. But the question we want to ask now, how are the model coefficient estimated? Well, like I said at the beginning, I said I actually want to unravel the mystery behind the scene. How do we actually obtain the 15.0429 and minus 0.2322? What is a statistical methodology that we actually use? Okay, that is the essence of today's work, the essence of today's lecture. Okay, I'm actually going to have a recap of what we normally do in linear regression model, where we are actually trying to assume that the relationship between the response variable and the predictors is a straight line. And when we actually plot the response variable against the predictor, we actually going to have what I call a scatter diagram, okay, which we call a scatter plot. And when you have a scatter plot, of course, we actually looking for the line of best fit. And of course, if different people, if we is to draw the line of best fit, it's actually going to look like this. Somebody can say, okay, this is my straight line. Somebody can say, no, this is mine. Somebody can say, because we're trying to connect points that are scattered away. So there's going to be possibility of lines. Okay, but you know what? The method we use in linear regression is actually called the method of the least square. Okay, the method of the least square will ensure that the straight line we're actually going to draw, okay, some other points we never that did not fall on the straight line will not be far away from it. Okay, it's going to be the one that we ensure a minimum distance, and that is why it is called a least square estimation method. I want to tell you, in linear regression, the method that we use to estimate parameters is actually the method we call the least square estimation method, because the method of the least square, the least square method actually ensure that the residual sum of squared is minimized. Okay, residual sum of squared is minimized. So the residual sum of squared is actually what we, abbreviated as RSS. Okay, so that is what um, the least square estimation method, ensure. Okay, we're trying to we are trying to estimate the beta 1 and the beta naught that minimizes the residual sum of squared. And you remember the residual sum of squared is actually the unexplained parts of the model. Even though we actually want to use our model to represent reality, but we know that model can never give exact reality. There's always going to be an unexplained variation. And even though we acknowledge the fact that there's going to be an unexplained variation, but we are actually looking for a method that that can guarantee a drastic reduction in the residual sum of square error. Okay, now if that is what we use in a simple linear regression, then now the question now is, do we also use the least square estimation method in figuring out the model coefficient in logistic regression? And my answer is no, we don't use that. I'm going to say that again. When you're dealing with the linear regression, we actually use a method of least square estimation, but in logistic regression, we don't use that. And I want to tell you now what we use, the method we use in logistic regression to estimate parameters is actually called the method of maximum likelihood. Take a look at this guy here. That is what we use in logistic regression to estimate parameters. But in linear regression, we use a least squared estimation method. Okay, before I move on, I also want to confirm again if everyone is still hearing me clearly. Is everyone still hearing me clearly? Okay, thank you so much. Thank you for confirming that. Okay, so like I said, we don't use the least square estimation method. We use the method of maximum likelihood estimation method in estimating parameter of, logistic regression model. Before I move to the understanding of the maximum likelihood estimation method, and before I explain how it is different from the least square estimation method, I think I would need to first discuss with you, what is this, what I have here. Of course, if you take a look at the model here, which is actually the probability form of a logistic regression model, if you plug in your beta naught, you plug in your beta 1, and then you actually plug in the values of S, based on what you're saying here, 60, 70, 80, and you're trying to plug in 60, you can determine your probability of damage. Okay, for every values of predictor, since you already know the regression coefficient, you can actually predict the probability associated with a particular predictor. And you know what, that will give you opportunity to make to plot. So what I'm trying to show you at this end is basically the probability, plotting the probability of the response against the predictor. And as you can see in the picture, you don't see a straight line, you see a sigmoid. That's a sigmoid. Okay, we call it a sigmoid. Okay, that's a sigmoid shape. Take a look at that, and that's actually binded in the range of 0 to 1. As you can see, it doesn't go beyond 0 to 1. And of course, when you fit linear regression, okay, when you fit a straight line, instead of you to fit a logistic regression model, it's actually going to go beyond 0 and 1, and that doesn't really make sense because we expect the range of the response variable to be between 0 and 1, because don't forget the response variable here is categorical. Okay, so that is that on that. But the next thing I actually want to walk you through now, okay, is to explain, what is the meaning of the maximum likelihood estimation method. Now, in the linear regression, like I said, we use the least square estimation method. And the reason why we use the least square estimation method, because that particular method will enable us to minimize the residual sum of square. But we're not interested in minimizing residual sum of squared in a logistic regression model. But what we're trying to do is to maximize the likelihood. What do we mean by maximizing likelihood? I'm actually, because of that, I'm actually going to walk you through what is the difference between likelihood and probability. Because when you look at the English dictionary, we have some, when you check online, some people may be thinking that, likelihood and probability can be used interchangeably. But I want to tell you there's a difference between when you say likelihood and when you say probability. Now, if I want to use a method of maximum likelihood estimation, then it means I actually want to find the parameter, I want to find the estimate of the parameter that actually maximize the likelihood. And that is the reason why when you look at the output, when you look at the code in R, okay, where you want to run the logistic regression in R, we normally use GLM, which we call the generalized linear model, because the logistic regression that we're trying to do is a generalization of linear regression model. And that is why we actually, instead of us to use the LM in the code for logistic regression, we actually use a GLM. Okay, so just like what I said, since I said the maximum likelihood estimation method actually find the values of the slope and the intercept and maximize the likelihood. But right now, I need to walk you through what do we mean by likelihood. Is it the same as probability? And I want to walk you through that now. And I want to tell you authoritatively that likelihood and probability, they may sound, or likelihood, they may sound the same way, but they are not actually the same. Okay, they are not the same at all. Okay, and I'm going to tell you why they are not the same. I want to tell you, we find ourselves in a world where there's a lot of variations. And of course, if I want to talk about probability, the probability is just going to tell me, or maybe I'm interested in the chance of the occurrence of a particular event within a sample space. Okay, that's what we mean by probability. It's like, you are trying to measure the degree of doubt, something like that. But when you talk about likelihood, on the other hand, okay, the likelihood, on the other hand, if you look at likelihood, okay, the likelihood of occurrence of an event could occur, it may not occur, even though they may sound the same, they may sound the same way, but they are not the same. But you know what, mathematically or statistically speaking, I'm actually going to walk you through the difference between the probability and likelihood. Number one, I'm actually going to start with direction. Now, with the direction, what we're doing in, when we're actually investigating, using a model, we talk about the probability of our model. Okay, because every statistical model is probabilistic. I'm going to say that again. Every statistical model is probabilistic. What makes a statistical model a probabilistic is because of the incorporation of a random component. Because we know that, it is, the model, even though we're using model to capture reality, but model can never be the same as reality. There must always be, error. That's what I mean. So the probability of the model now, okay, that's exactly, and the probability of the model is just, you are referring to the outcome, that come out from the data set that you analyze. But let me tell you something. We go from the probability of the model to data outcome when you are talking about probability. But when I'm talking about likelihood, I'm actually going to start from the data outcome until I get to the probability of the model. Now, if I really want to explain now, okay, if your theta equal to 0.7, you are given theta to be 0.7, and they say, what is the probability that I get 8 head in 10 independent coin flips? That would be a binomial distribution, because the binomial distribution, I told you, um, because of the response variable is categorical, of course, the underlying distribution of logistic regression is binomial. And when I say binomial, okay, the binomial is actually it's a probability distribution we use to model, a variable with two possible outcomes. I'm going to say that again. A binomial distribution is actually a probability distribution we use to model a variable with two possible outcomes. When you take a look at this example, when you have a coin, a fair coin, we got two sides, right? You got head, you got tail, right? And this example is trying to tell you now, if the probability of getting head is 0.7, because the theta here actually represent the probability of getting heads. Okay, when you flip a coin, probably a good numbers of time, okay, they realize 70% of the time, heads will actually show up. Now, having know that, okay, and you now want to figure out what is the probability that if I get, that I get 8 head in a 10 independent coin flips. That is, if I flip a coin 10 times, what is the probability that I'm actually going to see 8 heads? Okay, in that situation, you are actually finding probability. That's what you're finding. And the notation for that is actually going to be this guy here. And don't forget, given that you know that 70% of the time, okay, 70% of the time, okay, the number edge actually come up. Now, what is the probability that if you now take a coin, you flip that 10 times, okay, what is the probability that you're actually going to see 8x? Okay, now I want you to see the difference between that and when I'm talking about likelihood. Now, look at the way the likelihood is going to reframe the question. Likelihood is going to say, given that I got 8 heads, can you still confirm if you are hearing me clearly?
Yes.
Okay, thank you so much. You know why I'm asking, why I continue to ask, is because of network. Okay, so that is why I'm continuing. So in case you are not hearing me, or in case you need a clarification, it's either you chat with me or you can actually talk and by asking question. Okay, look at the likelihood, the way the likelihood is going to frame the same question. The likelihood is going to say, given that I got 8 head in 10 independent coin flip, what is the likelihood that theta equal to 0.7? And I want to tell you this and this are not the same. I just wanted to say in types of direction, okay, to see the difference between probability and likelihood. Now, if you look at the one said, given that theta equal to 0.7, okay, given that 70% of the time, okay, we normally see a when you flip a coin. What is the probability if I go and flip a coin 10 times? What is the probability I'm actually going to see 8 head? That is probability question. But when you look at the likelihood on the other hand, the likelihood is going to say, given that I got 8 heads in 10 independent coin flip, you've already gotten 8 heads. Okay? You've already flipped the coins 10 times and you got 8 heads. Now the question now is, what is the likelihood that theta equal to 0.7? Now, this is a notation for two of them. They are not the same. Okay, I just wanted to say that there's a difference between probability and likelihood. And you know what? Why am I explaining this? I'm explaining this because I told you we use the method of maximum likelihood in estimating the parameters of logistic regression model. And I actually wanted to say the difference between the likelihood and the probability. Okay, if you get that, and I'm actually going to continue now. Okay, I told you the theta actually represents the probability of the coin landing on the. Okay, to take a look at that. Now, I think I've walked you through the difference between the probability and the likelihood now. Now, what I want to do now is I now want to show you how we calculate likelihood and probability by hand. But I'm not going to ask you this in exam because you actually, if you want to estimate the parameter of the logistic regression model of any model, you're actually going to use software. But what the essence of this lecture is just to explain what happened behind the scene, how the parameters are actually estimated. Okay, you get what I mean, right? And that is the reason why I want to walk you through what happened behind the scene. Okay, now I want to walk you through how do we calculate likelihood and probability by hand. Okay, based on the example that I cited the other time, where I know 70% of the time, we normally gonna have heads when we flip a coin. Okay, and what is the probability that if I chose a coin 10 times, and what is the probability I'm actually gonna see 8 head? Uh, the formula that I'm actually want to use is what we call the formula of the binomial, which is actually big Y equal to that is, n combination Y, okay, or theta raised to power Y, okay, 1 minus theta raised to power n minus Y. Take a look at that. That's a binomial probability distribution. Take a look at that. Okay, now I know my n. N is the numbers of trial, which is 10, and y represent the numbers of heads, which is 8. And of course, you have been given your theta to be 0.7. Okay, you're going to see that here I've already plugged in, okay, the values of y, the values of theta, and the numbers of time the coin is tossed into the probability formula, and that gives us the probability that we got now is 0.233. So 0.233 is actually the probability that when you toss a coin 10 times, the numbers of time the edge is going to show up is actually going to be 8. Okay, given that the probability of getting head is 0.7. Okay, that is what I just figured out now. Is there anyone who actually need clarification, or is there anyone who want to ask question? Is there anyone who need clarification? If you really understand what I just explained now, I need you to comment yes or you say yes. I'm going to say that again. If you really understand what I explained now, I need you to comment yes or you say yes. Okay, I think I've seen people saying yes, but you know what? If you don't really understand, please ask question. You pay for the service and you deserve to be served better. Now, I've talked about probability now. Now, the next thing now is to talk about the likelihood. Okay, how do we calculate likelihood? Okay, I want to show you now how we calculate likelihood. We actually want to find the likelihood of theta given that y equal to 8. Given that the numbers of eggs that I got equal to 8 when I flip a coin 10 times. And I actually want to figure out, the likelihood. But you know what, if just like that is the same thing that we normally want to do when we want to estimate the parameter of logistic regression model. Okay, I told you we're actually going to use the maximum likelihood method, but you know what I want to walk you through now is how the method of how we figure out the method of maximum likelihood by hand. Okay, the manual way to do that. Now, when you take a look at this guy, that's what we want to find the likelihood of theta, given that y equal to 8. We are looking for the values of the parameter theta. Okay, so that's exactly what we're looking for. But you know what? In looking for the values of parameter theta that will maximize the likelihood, I'm going to say that again. We are looking for the value of the parameter theta that will maximize the likelihood. Okay, now it means among the values of parameter, it is not all of them that will maximize the likelihood. We now want to have an investigation now. Okay, now the investigation, let's say for instance, we have some certain values of parameter in mind. Of course, for logistic regression, of course, the theta is actually going to go from 0.1, 0.2, probably all the way to 0.9. It lies between 0 and 1. I think you know that, right? Okay. Now, but you know what? Let us suppose that the values we have in mind is 0.7 and 0.9. We're just assuming that. Why do we say 0.7 or 0 and 0.9? Because the other time here when we were finding the probability, we already know that the probability of the state of nature is 0.7. Because I told you the other time in class, our mind can never be empty. I'm going to say that again. Our mind can never be empty. We know we have something in mind, probably through experience. And that is the reason that's going to give us a clue on the values of parameter we actually going to consider, because there's a lot of values of parameter we can consider in the range of 0 to 1. Okay, but because our mind cannot be empty, then since the other time we have a 0.7 here, we can begin to actually search between the 0.7 and the 0.9. Why do I choose the 0.9? That is more or less the higher probability, because we're trying to say the random variable y lie between 0 and 1, and of course the upper part of the probability will be 0.9. Now you know what I'm going to do now. Okay, take a look at this guy. Okay, when theta is 0.7 and y equal to 8, I'm going to use the binomial formula again. Then I'm going to plug in that. When I plug in that the other time, of course, this is what I got, right? When it is not 0.7 now, if it is 0.9, and I use the binomial formula again, what did I have? Oh my God, that gives me 0.194. Now, which parameter give us the maximum likelihood? If you take a look at this too, I want to award an extra credit now. Okay, I just want to see whether you are following me. What values of the parameter give us the maximum likelihood comparing these two models? Can somebody tell me? What values of theta can you say maximize the likelihood? When I say maximize the likelihood, the values of the parameter theta that actually give the higher values of the likelihood. Can somebody tell me for extra credit?
Would it be theta is 0.9?
When the theta is 0.9, that gives us 0.194. When the theta is 0.7, that gives us 0.233. So which one is bigger? Yeah, somebody text a message, somebody share with me now. Somebody said the one that is going to be bigger is of 0.7, and that person is correct. Take a look at this. When theta is 0.7, what was the value that we got? We got 0.233. When theta is now 0.9, the value that we got is 0.194. If I want to choose the theta now value here, I'm actually going to prefer 0.7. Because the 0.7 is the values of the theta that give me the maximum likelihood. So right now, this is basically, this is a likelihood value. Those two are likelihood value. Okay. So, and in maximum likelihood, we're actually looking for the values of theta that we give that. Okay, so that was why I asked the question here. Look at that. And it is actually going to be 0.7 because of the fact that it has a maximum value for likelihood. Now, I want to apply this in logistic regression now. Okay, you know, the essence of doing that is how parameters are estimated. In logistic regression, I told you we got to use the maximum likelihood. But let me tell you, the theta, our theta here is going to be beta naught and the beta 1. It's going to be our theta. We're now looking for the values of the beta naught and the values of the beta 1 that will maximize the likelihood. Okay. Now you remember this is the the probability form of a logistic regression model. Okay. And of course, these are our parameters is beta naught, beta 1. And we've collected our data set, right? We got our data set, right? Where the response variable is categorical. And what are we looking for? We are actually looking for the values of the beta naught and the beta 1, given the data set that we maximize the likelihood. I'm going to say that again. We are looking for the values of beta naught and the beta 1, given the data set that we actually maximize the likelihood. Okay, what we're going to do now, you can actually begin by assuming, okay, if you let your beta naught to be 0 and you let your beta 1 to be 0.5, what happens? In the investigation of what values of parameter in the logistic regression that will give us the maximum likelihood, okay, we normally do a lot if you want to go manually. And that is the reason why you need to appreciate the software. The software that return results in seconds. Oh my God, I've done a lot, because if you want to do that manually, this is the way we're doing it now. That's where we're going to do it, and that is actually going to take forever. Now take a look at this guy here. You are given data set where you are looking at it. You can see y is 0, 1. Y is the response variable, is categorical, right? And you can see X, that's predictor, right? You are looking at the effect of a predictor on the categorical response. Of course, you're going to fit logistic regression. And right now, how do we estimate the parameters of the logistic regression model? Okay, and I want to walk you through how you can estimate that using the maximum likelihood. Oh my God, take a look at what exactly now it means. If I assume that my beta naught equal to 0 and my beta 1 equal to 0.5, okay, and of course, I got my data set, right? That is my response. When y1 equal to 1, 1, you can consider I'm using 5 observation here, 1, 1, 0, 1, 0. Take a look at that. Okay, so when I have that now, if I want to find the probability now, what I'm actually going to, if you take a look at this guy now, the likelihood is going to be okay, I'm actually going to find, multiply the probability together. I'm actually going to come here. Okay, take a look at this. I'm going to plug in beta naught, beta 1 into that equation. Okay, then when I plug in beta naught, beta 1 into that very equation, okay, for the first one, because I have 5 data points, that is exactly what I'm doing here. Take a look at this guy now. Okay, I'm going to have 5 of them. Why do I have 5? Because I have 5 observations. I'm going to say that again. If you look at the first one here, when y1 equal to 1, which is this guy, then I'm assuming beta naught equal to 0, beta 1 equal to 0.5. I'm going to multiply by the second one, okay, the third one, the fourth one, the fifth one. Okay, so if you take a look at this, I have 1, 2, 3, 4, and this is 5. Take a look at that. Now, I'm now going to use the probability model. Okay, the probability model form of the logistic regression is going to be in 1, 2, okay, up to the fifth one. But let me tell you this: when y equal to 1, it's going to be this. Okay, when y equal to 1, we're also going to have this. Do you know when y equal to 0, it's going to be 1 minus. It's going to be 1 minus 1 over 1 plus exponential raised to power this. Anytime the response variable is actually 0, you're actually going to say 1 minus that, because you remember that when the probability function that you are given is for when y equal to 1, but if y equal to 0, it's going to be 1 minus the whole probability, because the probability of success, the success and failure are mutually exclusive. Okay, that is why. So when you take a look at the last one, when y equal to 0, you're going to see. That is why you see 1 minus that. What am I doing now? What I'm doing now is to plug in the values of s equal to 5. Look at that. This is the first one. S equal to 7. I plug in that, the second one, until you get to the last one, s equal to 4. Okay, you now compute all of that. When you compute all of that, it's going to give you 0.19. This is not only what you're going to do. So what this guy is giving me now is the likelihood is 0.19 when beta naught equal to 0 and beta 1 equal to 0.5. You know what I'm going to do? I will continue to change the values of beta naught and beta 1. When I change the values of beta 0 to something else and beta 1 to something else, I'm still going to do all this and find the likelihood. But you know where am I going to stop? You know where I'm going to stop? I'm actually looking for the values of the beta naught and the beta 1 that will give me the maximum likelihood value. And that is what the R software was doing. That is what the R software, I want to tell you the software, the Python, the R software, and the like, they're really doing a great job, because if you really want to do this manually, of course, in searching for the values of beta naught and the beta 1, there's a lot of value we can search for, and we're going to settle with the one that gives us the maximum likelihood value. Right now, the maximum likelihood value we have, the likelihood value we have here is 0.19 when we have beta naught equal to 0 and beta 1 equal to 0.5. So which means we're still going to continue to choose different values of beta naught and beta 1. And in the process, we're actually going to be computing, we're going to be getting the likelihood. And at the end of the day, when we have considered the possible values of beta naught and beta 1, we're going to compare the likelihood that come out of that. And of course, we're actually going to choose the values of beta naught and beta 1 that give us the maximum likelihood. Like here now, the only one I just showed is this is just a situation where the beta naught equal to 0 and beta 1 equal to 0.5. And this may not be a maximum likelihood value until we actually try other, the or the range of values. We got to vary the beta naught and beta 1 and see whatever the likelihood value that come out of that. Okay, that is what happened behind the scene. And the reason why I'm trying to show you what happened behind the scene is not as if I'm not going to give you this in exam, but I'm just trying to, explain what happened behind the scene in the estimation of the parameters of logistic regression model, so that you will be able to appreciate the software you are using. Okay, the software you are using actually save time. Okay, because imagine if you are going to do this manually, you're actually going to do a lot. Okay, because right now what you're seeing us doing here is when the beta naught equal to 0 and the beta 1 equal to 0.5, it means we need to vary the values of beta naught and beta 1 to be able to compute the likelihood, and at the end of the day we're going to settle with the values of the beta naught and the beta 1 that give us the highest likelihood. And that is actually what we mean by the maximum likelihood, okay, method. This is going to be the end of my lecture today. I want to give room if you have any question you want to ask. Is there anyone who need clarification? Okay, before I go today, I'm going to say I'm in the process of grading, the practical tool. Of course, I think I should be done today. And of course, the midterm too as well. You make sure you check the course module. By tomorrow, you're actually going to see your result for midterm too. And of course, you're also going to see, I'm going to post the practice question for the final. Okay, make sure you stay safe and have a wonderful celebration, on the Thanksgiving. Okay, we'll see you next time. Bye for now. Yeah, thank you too. Yeah.